Demo Day. Today I'll be presenting how to factor polynomials with a common factor. This is kind of like the basics of factoring polynomials or quadratic equations, which gets progressively harder as you get polynomials with more terms. And there's a bunch of different strategies you can use to factor polynomials, but this is kind of like one of the most basic ways you can do so, primarily working with binomials and monomials, which we'll talk about right now. So first, what is a polynomial? A polynomial is an algebraic expression consisting of variables, also known as indeterminates, coefficients, and the operation of addition, subtraction, and non-negative integer exponents of variables. So these polynomials can have one or more terms. Isla, do you know what coefficients are?
Coefficients, aren't they like the 3x?
No, so it's actually the number that is being multiplied by x.
Right, yeah.
So yeah, if you see this example polynomial, 3 is a coefficient and 4 is a coefficient. It's basically,
so it's a number being
multiplied by the variable.
multiplied by a variable.
Yeah, so basically this polynomial is just one example, but it can, as you can see, this polynomial has 3 terms. It can basically have infinitely many terms, like however many terms you want, as long as it's greater than 1 or equal to 1. So that's what a polynomial is. And there are different types of polynomials classified by however many terms that polynomial has. So for example, a binomial is a type of polynomial that contains exactly 2 terms. So this is an example of a binomial is x minus 4. And this, while our definition of polynomial says it must have coefficients, technically x by itself still has a coefficient of 1. So that would count as a coefficient. So this is still a polynomial. And so as you can see, this consists of 2 terms, x and minus 4. All right, and lastly, monomials. A monomial is a polynomial with just 1 term. It can be a constant, a variable, or a product of constants and variables raised to a non-negative integer power. So this is just an example of monomial. As you can see, there's only 1 term. Okay, so as we move on, I include a couple videos on how to factor polynomials, but I'll be covering that later on in this presentation. First, I'll just outline a few applications of factoring polynomials. So of course, this can be used for solving polynomial equations. And so this allows you to break down the equation into simpler parts, and then you can also find the roots or the solutions of the equation. So the roots and solutions either means like you're finding a simpler way of expressing that same equation, or you are finding the solution to the variable or the indeterminate, as we already covered earlier. And so this can help with optimization problems in calculus, graphing polynomial functions, and identifying their roots or zeros. Then there's also simplifying expressions, integration and differentiation, cryptography, which I thought was interesting because I did cryptography in Python. Not quite so complicated that I needed polynomials for that, but I'd be...
What's cryptography?
Essentially, cryptography is just a field, I guess you could say in computer science, where you're trying to encrypt data so that hackers can't like hack information. Basically, as you're transferring data that's maybe really sensitive, like for example, let's say your banking application and you like have people submit their social security number, you don't want to just like be sending that social security number, you know, and then that would be very unsecure. And so you would have an encryption function that allows you to encrypt it so that, let's say, if hackers do hack into that information, it's just a bunch of encrypted mumbo jumbo. You don't really know what it says.
Yeah.
So that's what cryptography is. And so polynomials can be used to create much more complex and robust cryptography functions, encryption functions, unlike the ones I was doing when I was like 8 learning Python. But anyways, then signal processing, economic and financial models, control theory, and lastly, quantum computing. All right, so now we can get into some example problems. This is using some of the things that I was discussing in regards to the nature of exponents and how you can use them. So, all right. So in this example, we have these 2 boxes, and this monomial, as already discussed, is representing the area of each box. And from there, we can derive the length and the width, essentially factoring the polynomial represented here. So basically, as you know, if you just have the length of something represented by L multiplied by the width of something, that will equal the area, right? So because of this, we just need to derive what is the greatest common factor between these 2 polynomials. And so the greatest common factor for 55 and 22 is going to be 11. Both of them are multiples of 11. And so we know that the width is going to be 11 as a base, as a coefficient, and then also both of them share the variable x, so we can say x, and then the greatest common factor between both of these is to the power of 4. And the reason being is that when if you multiply x times 4, or x to the power of 4 times x to the power of 2, you get x to the power of 6, because you're adding 4 plus 2, right? So that's building off of what we talked about in one of my other presentations on radicals and rational exponents. So because of this, the greatest common factor between these 2 monomials is 11x to the power 4. So now, because of this, now we have the width, we need to get the length. So to do this, we'll say what multiplied by 11x to the power of 4 equals 55x to the power of 6. And this would be 5, right? Because 11 times 5 is 55. And then x to the power of 2. As we already covered, 4 plus 2 is 6. And this is 55 to the times x to the power of 6. And then this would be multiplied, or wait, sorry, no, multiplied.
Plus.
Yeah, it would be plus 2, because 11 times 2 is obviously 22. So then we don't need to add any variable or coefficient, because 2 times 11x to the power 4 is 22, x to the power 4, which is what we have over here. So now we have our answer. Oops. Yeah, so now we have our answer. The width is 11x to the power of 4, and the length is 5x to the power of 2 plus 2. And basically what this means is that if we want to represent this, this over here, we can just say 5x squared plus 2, wrap this in parentheses, multiplied by 11x to the power of 4 would equal the area of this box over here. You see that? So now we know the equation in order to get this box, just how we see over here in this equation, because we've identified the length and the width. Does that make sense, Isla?
Kind of.
All right, well, we'll do this for a few other examples. All right. Now it's a little bit more complicated because this over here has, this is basically a polynomial with 3 terms. 6 times n to the power of 4, 20 times n to the power of 3, and 14 n to the power of 2, or squared. So now what is the greatest common factor between all of these terms? What do you think, Isla?
Greatest common factor that what's a factor again?
Factor is basically what you can multiply together in order to get a final number. For example,
Is it like 12?
yeah. Okay, so let me show you. Let's say we have this number 12 and we want to know all the factors of 12. 1 times 12 equals 12, right?
Yeah.
2 times 6 equals 12.
Exactly.
3 times 4 equals 12. So now we have all the factors of 12, which would be 1, 2, 3, 4, 6, 12. And so when I say the common factor, it means what is the common factor for all 3 of these numbers?
Yeah.
That's the greatest common factor, right? Because of course all of them are able to be multiplied by 1, right? That's the greatest, that's a factor of pretty much every number, right? So
yeah.
But we want to find the greatest common factor. So what is the greatest common factor for all of these numbers?
I think a factor would be 12.
Is 6? Is 12 a factor of 6?
Oh, I was looking at the exponents. Whoops.
Nope, you're looking at the base numbers here. Because the exponents
What's
are
the common factor?
Okay, I'll give you the answer. The greatest common factor for these is I'm pretty sure it's 2. Correct me if I'm wrong.
Because you figure out the greatest common factor of 6, 20, and
Yeah.
14,
Yeah.
and then you figure out what's the greatest common factor of n to the power 4,
Yeah.
to the power 3, n cubed, and n squared.
Yeah.
Right.
So the greatest common factor of all these numbers is 2. And then all of them share the variable n. And then the greatest common factor here, you just need to find the smallest number, which is 2. And the reason why is because these exponents, the property of these exponents when multiplied to each other is additive. So if you have n squared times n cubed, you would get n to the power of 5. You wouldn't multiply these together. That's why that's why we can just find the smallest number. Does that make sense, Isla?
That's why we can what?
That's why we can just get the smallest number, right? Because obviously 3 and 2 don't share the factor of 2, the common factor of 2, right? The only factors of 3 is 1 and 3, which is why 3 is a prime number. And so because
another way to explain this, Isla say n to the power 4 is equal n squared times n squared. So assume if you write down this n to the power 4 is equal n squared times n squared. And then write down another
n to the power of 3 equals
n squared times n. And then n squared is equal n squared times 1. Therefore, the largest common factor of these 3 is n to the squared.
Does that make sense, Isla?
Yeah.
Okay. Thanks, Mommy. Yeah, great explanation. All right. So now that we have our greatest common factor for the width, we can do this for the length. And so 2n squared is times 3, right? Because 2 times 3 equals 6, and squared is equal to 6n to the power 4, right? Because n squared times n squared equals n to the power 4, and 2 times 3 equals 6. So therefore, 2n squared times 3n squared equals 6n to the power 4. Does that make sense, Isla?
Yeah.
Okay. So then we just have to do this for the rest of them. So 2 times 10 equals 20. So then I would put in 10, n, and then that's because n squared plus n equals n cubed. And then we would add plus 7, which because 2 times 7 is 14. And then that's it, because we already have n squared here, and we have n squared here. So this is already a shared.
Wait, I don't understand where you're getting 10 and 7.
Because we're multiplying this width, because you see how we have the width and then we have the length. Width and the length. And you have to multiply these both together in order to get the area, right?
Yes.
And so we're multiplying, we know the width is 2n squared, right? So 2 times 3 is 6, right?
Yeah.
2 times 10 is 20, right?
Yeah.
2 times 14 is 17. Is 7. Sorry. 2 times 7 is 14. You see that? That's how I'm getting those numbers. Are you still confused?
No.
Okay, cool.
Also, one thing is that, so the area is actually area of 3 rectangular. And for these 3 rectangular, you have the same width, but the length is different.
Yeah.
The final length of the large rectangular is the length, the sum of the length.
Of these, is all of these together. Is the length. Does that make sense, Isla?
Yeah.
Okay. So now if we were to write out our final expression, it would be 2n squared, whoopsies, I don't need it, times 3n squared plus 10n plus 7 is equal to 6n to the power 4 plus 20n cubed plus 14n squared. Does that make sense? Because we have our width over here, which is 2n squared, multiplied by the length. Okay. Okay, cool. Awesome. All right, so now we're moving on to a bit more complicated. We don't have a visual anymore, but it's the exact same concept. We want to get the greatest common factor of these terms, and then we can multiply that, find out what we need to multiply that in order to get this final answer, and then we can factor this polynomial. So the greatest common factor of these numbers is also 11. So I'll take the width. I don't know if I necessarily need to say width anymore, but
Isla, do you understand that the greatest common factor of 44, 66, and 77 is 11?
Yes.
Okay.
so now we have,
It's just been a while since I learned about that.
yeah. And then they all share the variable k. And then we have the smallest number here is k cubed, right? Does that make sense to you, or do I need to explain it?
Makes sense.
Okay. And then we'll get the length, which is 11 times 4 equals 44. Then we need k squared because 3 plus 2 is 5. Then minus 6k plus 7. Because 77k cubed, we already have the k cubed over here. Right? Does that make sense?
Yeah.
So this is an equivalent expression. All right, awesome. We can move. And we have another example. This is us, we're factoring a binomial here. So if we see the greatest common factor between these two is 6, because 3 times 4 is 12. And 6 times 2 is 12, and 6 times 5 is 30. And so if we have the greatest common factor here is going to be 6k cubed multiplied by 2 minus 5k. All right. So does that all make sense, or? Because 6 times 2 is 12, and then plus this k squared, right? Because 6k cubed times 2 is 12k cubed, which is what we have up here. And then 6k cubed minus 5k is going to be, 6 times 5 is 30 k cubed, because k squared times k equals k to the power 4, which is what we have up here.
You are saying k squared instead of k.
Sorry, k cubed. All right. Let's keep going. All right. Last question we have here is 3b to the power 5 plus 15b to the power 4 minus 18b to the power of 7. And then the greatest common factor between all of these is 3, because 3 obviously is a factor of 3, because 3 times 1 is 3, 3 times 5 is 15, and 3 times 6 is 18. So we have the greatest common factor of 3b to the power of 4. That's the lowest number here. And then multiplied by 1b, or just b, because 3b to the power 4 times b is 3b to the power 5, right? Because the exponents is just b multiplied by itself how many times, right? And then you just multiply, just like you have 3 to the power of 3 times 3 would be 3 to the power of 4. Because if you expand this, it would be 3 times 3 times 3 times 3, right? Right? Okay. All right. And we can continue. Plus 5, and we don't need to add a b because we already have b to the power 4 here, minus 6b to the power of 3 is 4 plus 3 is 7. And so as you'll see, factoring polynomials just requires a strong understanding of, well, one, you'll need to know the properties of radicals and rational exponents. But mostly it's just learning the distributive property, because if you have something to this effect, basically you're just distributing this number into each of the items within here, right? Which is exactly what we're doing here when we're factoring, just in reverse, right? Does that make sense, Isla? We're basically doing the distributive property in reverse when we're factoring this.
Yeah.
Right? Okay, so that is how to factor polynomials with a common factor. As you later on progress in algebra, you'll learn multiple ways of factoring polynomials and how to do this with other kinds of polynomials. But yeah, great job, Isla. Thank you.
Good job, Sumay.
All right. Do you guys have any questions or comments, or should we move on to Isla's presentation?
I want to draw a connection because you said
Sure.
this is useful for the optimization problem.
Mm.
I remember when I was talking about these machine learning models, I teach computer to do a trick to achieve a goal. Like when we teach a dog a trick, right? There's the treat you give the dog to learn the trick, and for the computer, that's you also give computers a treat when it tries to achieve their goal, right? You give computer treat, and the treat is sometimes the function of the treat is a polynomial function. So that's why it is one example of why this is used for optimization problems.
Interesting. Yeah.
Because when you try to teach computer to achieve a goal, it's essentially an optimization problem.
Right.
And you use the criteria for optimizing is like the treat you give to the dog when it does the trick.
Right.
I don't see how the polynomial.
Is it that the treat is is it that you're rewarding it for a lower error rate?
Yeah.
Okay, so basically, Isla, if you have the computer will predict something, and then when it falls short of that prediction, either if the prediction is like too low or too high, then there's like an error margin. And basically the way it's like, let's say you predict that Sally is gonna grab 5 cookies out of the cookie jar and she only grabs 5. Your model of prediction was wrong by 2 cookies. That's the error margin is 2 cookies.
You meant 3.
Yeah. So I said that she grabbed 3. She only grabbed 3, and you predicted
5.
Oh, really?
That
Whoops.
confused me.
Sorry. Okay. So if you predict 5 and she grabbed 3, that means that it was off by 2, right?
Yeah.
And so that would be your error margin. And basically
It's actually called the margin of error.
All right, margin of error. And so you basically, the treat that you're giving the computer is saying that the lower that your margin of error is, the better it is, right? You're telling them that that's your objective, is to lower that margin of error.
If it's a margin of error,
See how polynomials work.
I believe, correct me if I'm wrong, that essentially a polynomial, if you graph a polynomial, it is a curved graph. Like if you have linear functions are way simpler than if you have a curved function, right? And so when you graph a polynomial, you see this curved function. Essentially, that can be graphing the error, margin of error.
So considering there is a curve that's like this, like a little mountain,
right?
It's a polynomial function, right?
Mm-hmm.
And then there's a peak of that mountain. You know, sometimes you want to your goal is to reach that peak of the mountain.
Yeah, it's basically like you have a relationship between these two variables that isn't linear. And let's say if you're trying to see, like, given what input do I get the highest output or the lowest output? So if you're trying to lower the margin of error, then you're saying, like, given what input or what prediction model can I get the lowest output or margin of error? And that's going to be graphed in a polynomial function generally, if you have like if you're trying to solve a complicated function,
wouldn't it be like this?
Yes, that's true. It should be a valley.
It could be
like a valley, not a mountain.
Right.
So it's actually one of the.
If you're graphing the margin of error, if you're trying, there are some cases in which maybe you're trying to get like the highest amount. Like it just depends on the problem you're trying to solve.
Yes. Good point, Eilert. In this case, the function is like a valley.
Yeah.
Instead of like a mountain. So you want to get to the lowest point of that valley.
And then there are also one thing you'll learn in algebra is how do you mathematically find the highest or lowest point of a polynomial function. So